So our next presentation is Juliane Gross, and she's going to be talking about the gift that keeps on giving, that is lunar samples.
Thank you, Julie. And I'm going to jump right in. So if I could have the next slide, please. Great, thank you. All right. So we all know that the moon is the most accessible place in our solar system to study planet-altering processes, and because it is largely inactive, the crust has recorded and preserved the geologic evidence of these processes since its formation. And that's why we call the moon a museum of planetary history. Now we have direct evidence of these processes in the form of rocks and samples that have been returned to us by humans or by nature in the form of meteorites. And we have indirect evidence that is provided through chemical signatures, for example, hydroxydophile elements or isotopes. And these provide us with information about processes such as core formation or accretion, mantle melting, even degassing in the volatile cycle. Now, we all know that the moon is also a space probe and time machine because the regolith on the surface has been interacting with the solar wind and galactic and cosmic X-rays over billions of years and has recorded, so to speak, our solar system climate and our solar system climate change over billions of years. And so all this information is basically stored in the crust and the regolith, and therefore the crust is basically an archive, and we just need to learn how to read and interpret this archive correctly. Next slide, please. So it's not surprising that the lunar crust has become one of the most well-studied stagnant liths in the solar system, and also serves now as the cornerstone for understanding lunar crust formation on other terrestrial bodies. And the 382 kilograms of rocks that were returned during the Apollo missions have played a really crucial role in this. And so these returned samples either represent pieces of the primary crust, as you can see here, this beautiful Apollo 16 anorthosite, or if we go to the next slide, please. There are additions made to the crust, either through endogenic processes such as, there are modifications to the crust, for example, through impact processes that create breccias, and you can see here these Apollo 16 breccias. And breccias are really treasure troves that contain a lot of information. And then next slide. These samples can also be additions to the crust that were made either through endogenic processes such as volcanism that can produce Mare basalts that you can see here in the Apollo 11 basalt, or through exogenic processes such as fragments of other solar system bodies that were delivered to the moon, and those provide direct evidence of types of materials striking the moon at different times throughout its history. Next slide. So even though we just celebrated the 50th anniversary of Apollo, the samples are still in high demand. So here in this diagram in orange are the sample requests since 1984, and in blue are the allocated samples. And you can see that the overall demand has not declined. And to date, we have had 3,000 sample requests, and more than 50,000 samples have been allocated. So they're still going strong. Next slide, please. And so just to highlight the scale of the samples that are out being studied, and I literally, with Ryan, just looked up the new numbers last night. So currently we have more than 19,000 samples out to more than 430 lunar PIs in 24 different countries. And from the pie chart, you can see that most of the lunar PIs are located in the US, but other countries like the UK, Japan, France, and Germany, they all have substantial amounts of lunar PIs and samples that are studied in their respective countries. All right, next slide, please. All right, so this is not super surprising because the Apollo samples have been crucial to all of lunar science, which is basically anchored through these Apollo samples. For example, the Apollo samples are crucial to calibrate our remote sensing instruments that orbit the moon. Through Apollo samples, we were able to turn the crater count-derived relative ages into absolute ages. And so basically refine and calibrate the crater dating technique that is now used to also estimate ages of other planetary bodies throughout the solar system. And then the sample properties such as density and porosity and also the magnetic properties, they help us interpret global data sets from missions such as GRAIL, and they can provide constraints on the lunar dynamo or former dynamo. And both of these will inform us about the interior structure of the moon. And then we have the geochemistry, which basically includes everything from isotopes to bulk composition to mineral chemistry, you name it, like the list goes on. And that gives us a wealth of information that ranges from accretion to lunar formation evolution, including the lunar magma ocean, core formation to volatile cycles, space weathering, organic, and so on. Apollo samples have also helped us to recognize lunar meteorites, which are on average more representative than the returned Apollo samples. And these meteorites expand our view of crustal evolution and lunar formation beyond of what we have learned from Apollo. And then we have the exogenic material and particles, which include cosmogenic and galactic X-rays that are stored in the Apollo regolith. And those help us understand early solar system processes, the solar system climate and environment, and even give us information or insights into processes that lie beyond our own solar system. All right, next slide, please. So these Apollo samples still continue to reveal new information because we have better and newer and higher precision techniques and models. And so by using new technologies like the X-ray computed tomography or XCT scanning of the samples, like here's an example of the Apollo 16 breccia. By doing this, we can identify class within the samples without breaking them. So you can see in the CT scan that is highlighting potentially basaltic class in blue, and then in green we have iron-rich metals. We can also use this technique and scan returned and unopened drive tubes before they are opened, like we have done with the ENGSA program, where we CT scan the drive tube 73002. And with that, we can identify potentially new lithologies that are either in breccias or detect maybe textures or potential stratigraphies in these core samples. And so we get a glimpse of what to expect before we open these drive tubes. And all this information helps us to better identify samples of interest and then advise, advertise, and allocate those to the lunar community. Next slide, please. And new lithologies are still found in the lunar regolith today. Here's an Apollo 11 picture. And the regolith contains tens of hundreds or more millimeter to centimeter size rock fragments. And those still reveal new information about the moon. So just like a grab and go regolith sample is really important. Next slide, please. And then, of course, now we have opened access to specially curated samples currently through the ENGSA program that includes the 73001 and 2 drive tube, of which we have opened 73002, the upper part, last year. And I'm sure Chip will talk more about this in his talk in more detail. But on the lower left, you can see the extruded core. And then the picture above has the images of the particles that we sorted out of one of the intervals. And they're sorted into their respective size fractions. And so we CT scan all the particles that are larger than 4 millimeter, which are the 2 largest particles in that image. And we CT scan them individually. And you can see one of those images of the CT scan on the right side, which is a regolith breccia that has some particular glutinate or glass still attached to the outside. So by doing this, this gives us an incredible data set that helps us help the science team and then later also the lunar community to select the best particles that they need for their specific study. Next slide.
1 minute.
Gotcha, thank you. All right, so even though we have all of this new information that is still coming out of the Apollo samples, including regolith soils and rocks, we really still need more samples, specifically samples from areas that are different than Apollo, that also include the geologic context, right? We have meteorites and they're great, but we don't know where they're coming from. So we don't have that geologic context. So here's a list of different samples that would be fantastic to be returned because we don't have them in the current sample selection and collections. And this list is based on talks that were given during LPSC 2019. And some of those were already touched on yesterday during the breakout sessions and the talks. And today We heard Clive and Jamie already talk about some of those as well. And that's a huge range of different samples that would be fabulous to return. And so I'm just going to leave you with this slide and stop right here. Thank you.